When dealing with uncertainty of a function, then there's a big question that comes up of whether the variable that we're dealing with in the equation, in the function, is dependent or is it a single variable? So since we'll do it a flowchart style, so is variable dependent or single variable? So if it is not, then we have several series of rules here, which are relatively simple. And this is the more complicated one is if they are. Let's deal with the simpler ones. So, are we multiplying by a constant? Which actually works for a single variable as well. Then yes, distribute. So for example, I'll come back to that. If I have a variable, let's say length, which is 5.0 meters plus or minus 0.3 meters, and I want to figure out what twice that is, so 2 times L is just 2 times 5 plus or minus 0.3, or 10.0 plus or minus 0.6 meters. And just a side note here, I would either write, since meters applies to both of them, if I'm putting it out here, I need to put parentheses around this, or 10.0 meters plus or minus 0.6 meters if I'm expressing it separately. Don't drop the parentheses and just have the M out here. So if I'm multiplying by a constant, then just distribute. So now, and it's possible that you'll distribute and then you'll come back around again, but no adding or subtracting. Yes, yes, then add absolute uncertainty in quadrature. I'll write that one out just in case it's the first time you've seen it written out. Quadrature, and let me actually write it a little bit more neatly. Quadrature. Now, when we're talking about the absolute uncertainty, in the example that I had just given right there, this is the absolute uncertainty. It has the same units as this usually. If not, then it gets a little bit funky, but I recommend keep it in the same units. So this is the absolute uncertainty as opposed to the relative uncertainty, which we'll deal with in just a moment. I've taken measurements of 2 pieces of yarn. I want to know what the total length is. So length 1 is, we'll just keep it at 5 meters, 5.0 meters plus or minus 0.3 meters. Length 2, 3.0 meters plus or minus 0.2 meters. Now recognize what we're saying here is that the length is within 0.3 meters of 5. Now, this value right here, that's a separate video determining how to determine that value. But if I'm adding these, I have L1 plus L2. Now I'm adding these 2 right here. Recognize that there's a distribution here. It's not constant. Just as likely to find something above 5 as below 5, just as likely to find something above 3 as below 3, assuming I've done my measurements correctly. And so when adding them together, these are independent of each other. So I could have something above here and below here, or above and above, or below and below, or whatever the third common, I guess below and above, that's the fourth one. And so when I'm adding it, I'm not adding these straight up. So what I would get is first add the easy part, 8.0 meters plus or minus, and then adding in quadrature, 0.3 squared plus 0.2 squared. It's kind of like Pythagorean theorem, and you can probably connect it to that if you get into the statistics well enough. And so we end up with 0.80 meters plus or minus, and then pull out a calculator or use tables or slide rule, whatever you want to do, 0.360. That's more significance than I need. So 8.0 meters plus or minus. It's 2 significant figures. I'm going to go with 2 significant figures here. Actually, that's 1 and 1. Ugh, I hate significant figures. So 0.4 meters. if we care about significant figures. Now recognize that when you're dealing with significant figures, that is for presentation, that is not for computation. Now recognize that when you're dealing with significant figures, that is for presentation, that is not for computation. This is what I'm going to use for computation, or even take it out further, so 5, 5, 1, 2, 7, 5, 4, 6. But this is purely for presentation, not for calculation. And so that's how you add in quadrature. If I was trying to find the difference between the two, and I was a track, so I have 5.0, I don't have to write units while I'm doing the math, minus 3 plus or minus 0.2, then 5 minus 3 is 2.0. Plus or minus, when adding in quadrature, it's the same thing as there, so it's going to be ultimately 0.4 meters. All right, so back over here. Then you double back. And any more addition and subtraction? No. All right, move on. So multiplication, division. Yes. All right, so now we add relative uncertainty in quadrature. And what we're doing with that, so let's say that I've taken some sort of rectangle here, I've measured the length, I've measured the width, and let's deal with, numbers that are not whole. So 4.3 plus or minus 0.6 meters. We'll call that the length, and the width 3.72 plus or minus 0.34 meters. And so the area of this, I'm obviously multiplying. So 4.3 plus or minus 0.6, 3.72 plus or minus 0.34. Now, I'm going to go ahead and multiply these together. So 4.3 times 3.72 plus or minus 4.3 times 3.72 times, and this is what we're going to multiply, find in quadrature, is the relative uncertainty. In other words, the ratio of this to this. Now recognize that when we're adding and subtracting, presumably we're dealing with common units here. In this case right here, we're dealing with meters. And so we could add them up since we're adding things of like quantity. But here, these are not necessarily the same units. So adding these together or squaring them and adding them doesn't necessarily yield anything with which we can work. And so I need to basically make them unitless, 0.6 over 4.3. Since they presumably have the same units, I'll divide squared plus 0.34 over 3.72 squared. This will give us the relative uncertainty. And then you multiply times the median value, or the mean value, which is one of those two. And so this part right here is 0.1668039, and so on. I'll hold that off on the side for just a moment. And so this is 15.996 meters squared, plus or minus the relative uncertainty times that value, 2.668 meters squared. Obviously, I ignored significant figures here because that's what I felt like doing right now. Now, if I divided, for some reason I wanted to do a division of 4.3 plus or minus 0.6 meters divided by 3.72 plus or minus 0.34 meters. A comment earlier, I talked about the fact that these are not necessarily the same units, and recognize in this case they are the same units, but they are not necessarily going to be the same units. So when I'm dividing, I got 4.3 over 3.72 plus or minus that same ratio, 4.3 over 3.72, times the relative uncertainties added in quadrature. Just because we're dividing here doesn't mean that we're doing anything different here. Similar to when we added and subtracted, adding and subtracting does not change the fact that it's still a plus sign. That's an underscore right there. It's still a plus sign under the radical. And so 4.3, 3.72. So this becomes 1.1559 plus or minus, and then that 1.1559 times that, 0.1928. Oh, and that's that the meters would cancel out, so this would have no units. back to the flowchart. Single variable or independent variable. This has a relatively simple formula on the surface of it, assuming you know calculus. The uncertainty in y, so if we're dealing with y as some function of x, the uncertainty of y over the uncertainty of x is equal to df dx. So let's actually work through an example on that one. All right, so suppose I have y is equal to x cubed. Then the, actually, we're dealing with uncertainties here. So this is the basic function we're working with here. So how about y plus delta y is equal to x plus delta x cubed. Now this is the uncertainty right here. And so my uncertainty in y over the uncertainty in x is basically equal to the derivative of this, which is 3x squared. So the uncertainty in y is going to be 3x squared times the uncertainty in x. So if I have 4 plus or minus 0.2 cubed, please do not cube that and then cube that and just stick plus or minus in between it. Don't do that. This becomes 4 cubed plus or minus the uncertainty, which would be 3 times 4 squared times 0.2. So the 3 comes from here, basically comes from that. The 4 squared is because that is the value of x, and then that is the uncertainty. And so this becomes 64 plus or minus 9.6. If we're dealing with a square function, and it's very similar to what we just did, but there's a slightly different form that sometimes you see for squares. Then the uncertainty in y over the uncertainty of x is equal to 2x, which means the uncertainty of y is equal to 2x delta x. This is the form using the formula that we talked about, using this formula. This is where we get. Sometimes you'll see it written slightly differently, where if I have x plus delta x squared, that's going to be x squared plus or minus x squared times delta x over x times 2, the exponent right there. And so this ends up being x squared plus or minus, well, that cancels out with one of those, and you're left with 2x delta x. This is, you might consider it a shortcut. It might be the long cut. It depends on how your mind is working at that particular moment, but you do end up in the exact same place as you did before. So the 2 times x times delta x. To me, the delta y over delta x is equal to df dx, where y is equal to f of x. That makes more sense to me. Now let's actually apply it in one more case. Let's deal with trig functions. And so if I have y is equal to cosine of x plus delta x, and I guess that'd be y plus delta y, then I can find my delta y here, find my uncertainty in the value of y. I know that delta y over delta x is equal to df dx. So I'm taking the derivative of cosine, which is negative sine. So the uncertainty of y is equal to negative sine of x times the uncertainty in x. And so the cosine of x plus delta x, and that's a c there, is equal to the cosine of x plus or minus, should be a plus or minus there, cosine of x plus or minus negative delta x sine x. Now this minus sign right here comes through from the derivative, but we have a plus or minus right there. Sometimes you'll see this, the plus or minus and the negative sign there flip to minus plus, and sometimes they'll just absorb it into it because negative plus and plus minus really means the same thing. And so cosine of x plus or minus delta x sine x. Now we do need to pay attention to units here. That sine of x and cosine of x, those are just ratios. They have no units at all. And so since this term right here has no units, this whole term must have no units as well. And since this is unitless, that has to be unitless. And so when you're dealing with something like this, since delta x has to be unitless, this has to be in radians. If you're dealing with degrees, you're really going to get messed up there. And I think that sums it up.